let's dive into this conversation. Welcome to Omife Technology. And today we are looking at integrating vision and large language model for emotional aware robotic interactions. As we all know, it's very fun to actually want to talk to robots, but it's more fun when robots understand how you feel and your current mood at the moment. Now, we know that robotic has really advanced to understanding what human actually wants at every conversation. More like you're talking to a human, you always want to know when they are enjoying the conversation. You always want to know when they are feeling all right in the conversation, when they are in the conversation, and when they are not in the conversation. So we want our machines, our robotics, we want to design machines that will actually do the same thing that human feel, because it's very nice to interact with a machine or a system, and the interaction keep going, and they know when you are not in that conversation any longer. So as robotic engineers, this is what we want to achieve. We want to be able to design these systems so that they can understand how human feels. And how do we achieve this? Again, this is an introductory class. We'll just look at the surface. And maybe when next we meet again, having this conversation again, we can dive deeper into more technical aspects of this conversation. All right, so in this conversation, we'll be looking at some items. And what we have, we look at introductions and core components overview. We look at emotion detection pipelines. We look at chat interaction systems. We also look at robot emotional expression learning system. Now, this is where the robot tends to learn your current mood and be able to replicate this mood into their own system and perform exactly what you two are doing. And also look at technical performance optimization, and we'll look at the real world applications, and then we'll look at how these systems helps humans and achieve these interactions. All right, so let's look at this part. So in recent years, the fusion of computer visions and large language model has led to the emergence of highly interactive and intelligent systems. We all know that before now, we used to have robots that can just do some basic activities. But with the emergence of these technologies, now we now have highly interactive robots that can not just say anything they feel like, but that say intelligent, that engage in intelligent conversations. Now, we are having this conversation because we can actually perform this as humans. Now, machine can actually do this with this technology. With the vision, they can sense our environment, they can understand what is around them. With the large language model, they can interact and give meaningful conversation, textual, meaningful conversation. Now we said robot, particularly humanoid and service robot, now demand not just visual perspective, but contextual language understanding to interact meaningful with humans. Now, just seeing alone is not enough to help people to interact with humans or see their surrounding. With large language models, we can actually have a meaningful and intelligent conversation. Emotion recognition powered by computer visions and the conversational intelligence of large language model are jointly enables emotional intelligent robots. Now, large language model can able to understand this emotion that is extracted from computer visions. Now, the work of computer vision is to be able to detect how the human feel by using cameras and training convolutional neural networks to be able to detect patterns or embeddings on the facial expression of an individual. And these ones are fed into large language model that will make meaningful insight of this particular expression that is expressed by humans and be able to tell the robot the kind of conversation to have with that particular human so that the flow will keep going and the conversation will be very much intelligent. All right, it said we explore effective corporate virtual emotion. You agree with me that it would be very nice that you are conversing with a robot. They can make the interactions very lively. they can make the interaction very nice and very calm. Another human, not talking to a machine, right? All right, so let's look at some components. Now, what are the core components of these particular systems? Now, the core components of these particular systems are the vision modules and the large language modules. Now, to enable robots to interact meaningfully with humans, especially in emotion intelligent context, the system architecture integrates both visual perspective and language understanding. Now, we can see the vision module. Now, the vision module, what are the core components of the vision modules? We look at the face detection, where we have a model that can actually extract the embeddings or the feature of the face, where we understand how these patterns have been extracted, how a human feels, if the woman is happy, if a human is sad. Now, those patterns are extracted and fed into a learning model that will be able to learn this pattern and extract what the emotion of that particular person at the moment is. Now, we have this classification. When these models are being fed with this data, they are being trained with several hidden convolutional neural networks. Most of them are trained with, what we do actually train with convolutional neural network, because most of this architecture is very accurate and can actually extract some of this feature very well. I said the emotion classification, we determine the emotional state of a user based on the facial expression and other facial clues. Now, this is actually where the model actually extracts the features of an individual from the data, and the model learns to recognize these patterns. And this pattern are later fed into the models, and we use that after training to make inferences and be able to get the current state of the human facial expression. Also do scene analysis, understanding contextual information from the surrounding environment, not just capturing the face alone. We also be able to feed the robot or the model the scene in that particular environment to know the environment and be able to react intelligently to the particular scene. And we're also looking at the large language model. We know that the emergence of this large language models like the chat, the GPT-4, the Llama models, and the cloud models, and all of that. These models are trained based on the encoder and decoder architecture, transformer-based frameworks. They understand user prompts and natural language input. They generate appropriate and context-aware response based on the prompts you are giving them. They integrate visual clue to enhance relevance and empathy of their interactions. Now, this model are trained on large data. With this large data, we're able to get meaningful interaction based on our user prompts to that particular model. Now, how do we interface these large language models and visual models to create meaningful insight on a particular data? Now we look at the integration strategy. Now, see, the challenge lies in combining visual and language capability to create the unified intelligence systems. Now, we look at two main integration strategies that we can employ to achieve this particular task. Now, remember, the task is to be able to create meaningful insights in our conversation, our day-to-day conversation with robots, right? And now the key thing we're looking at multimodal learning and cooking level fusion. Now, when we talk about the multimodal learning, this is when a robot learns from a combined set of training. Now, what do I mean by combined set of training? This involves jointly training and combining visual and language embeddings. Now, this is when during our data gathering and processing, we can actually get our visual data and our textual data embeddings and train this model to understand both. All right. Now, this actually creates a very large model, and most times we have issues with trying to run this model in our low-level controllers and all of that. But when we talk about the token level vision. Models like Mini GPT, and let's say Llama 3.1 and all of those models. Now, we have this model trained separately. We have the visual model that is trained, and we have this GPT that are trained on textual data. And we have models like CNN that are trained on visual data to understand the emotional expression of a particular individual. Now, these features are takenized directly into their prompting. Let's say we want to get the emotions of a particular individual. Now we train a CNN model to actually extract these details, or to extract this the facial expression of a user. Then we impute this data into the prompting of models like GPT or cloud AI, cloud models, and also Llama models. And by then we can actually understand how a user feels and be able to interpret this visual input in line with the textual instructions and dialogue to create intelligent conversations. Okay, we'll look at the emotion pipelines. Now, doing inference, what we get is we have cameras that actually captures real-time video feeds and understand and take this this feed and pre-process them. While we process them, we get a model that actually extracts the embeddings of the face, and we use models like the MTCNN models that can extract the facial details or the embeddings of a human and fed this one to a particular model. So let's say a CNN model or a reasoning model that can actually learn these features and make meaningful predictions from there. And this model we use, like a CNN model that classify these emotions, or we can also use lightweight transformer model. But we want to achieve a real-time predictions, right? So we use lightweight model that are not too heavy. Depending on your data though, we use lightweight models so we can achieve real-time processing of this particular data that are coming from the camera. Now, what will be our output? Our output will be an emotion label with high confidence level. As you can see, you can achieve something like this with this model. After being processing and getting feeds from the camera, we feed this data into our model that is already trained on high accurate data that were extracted during the embeddings and fed them into a model and train them to learn these processing. And during our inference, we can feed this model with our processed data that are coming from the camera to achieve a high confidence level of the particular emotion. That emotion can be happy, angry, sad, depending on the particular emotion of that individual. Now we look at the chat interaction of these systems. We look at the language backend, where we can use our GPT-4 or Llama 3 or cloud model. This model can either be deployed locally or the cloud-based. Now, the key components of these interactions rely heavily on prompt engineering. Now, using the emotion state to guide the LLM behavior. Now, we are able to achieve this integration and this intelligent interaction by using a good and refined prompting and feeding the emotion that was detected from an emotion pipeline into the prompting so that the robot can understand the particular emotion of that individual. Let's say, now look at this example prompt. We have like, you are a compassionate robot assistant. The user appeared to, now, if you see this bracket, we have emotion. Now, these emotions are fed in real time from our emotion detected model. Now the response in real time and according to the emotion that is fed. Let's say, for example, you are conversing with the robot and your mood is you are not very happy at the moment. Now the model picks your facial expressions and feed it into our model to make predictions and send it to a large language model that will respond intelligently and keep a good conversation with you. Now we combine these models together. There are several models that have proven very good in terms of combining these emotions and the language embeddings together. There are several models who have proven very high, who can give us good accuracy. Models like the GPT-4, the Llama 3.5, most of these models are trained with high data that can actually understand some of these emotions that are being fed into them. Okay, now look at this example. Let's say the user enter a prompt like, I just don't feel motivated. Now, since our emotion detection system is running concurrently at the background, now when a user says something like this, now those models actually picks their facial expression and feed into the system. Now the system will respond intelligently and is able to lighten up the mood of that individual, or able to create an intelligent conversation that will lighten up the mood of that individual, and thereby creating a good sense of humor between the person and the machine. More like trying to balance the situation whereby it doesn't look like you're interacting with a robot, it looks like you're interacting with a human. And that way it will help us to create a very good rapport with the machine, making it feel as though we are interacting with humans. Now, robot emotional expression learning system. Now, robot will just see and interact intelligently with how you are feeling. Now, we are able to train robots that can actually mimic these emotions and learn from how you feel, and also make a conversation, create nice gesture that will keep you in the conversation and make you feel all right. So how do we achieve this? We have a facial expression engine. We also have voice modulation systems, and we have body language interactions. Now, not just looking at you without doing anything, a robot is able to mimic this expression from their facial look. They are able to mimic this expression from the tone of their voice, and they are able to mimic this expression not just by their facial look, by the tone of their voice, also by their body movement. We'll look deep into all of these modules and see how robots are able to achieve all of this functionality with what they have designed on them. Now, I want us to watch a video and see how some of these robots perform this activity.
So Ameca, a groundbreaking robot from Engineered Arts that talks and mimics human expressions and movements, now draws too, making it a fascinating blend of tech and art. This AI robot looks like a human but doesn't have a specific gender or race, with a gray rubber face and hands. It can move its arms, fingers, neck, and face, letting it show emotions and even talk. With microphones, cameras, and facial recognition software, it can interact with people just like a human. Now, recently, OpenAI and a Norwegian.
If you look at this video, we see that Ameca, she has 42 servos motor running on her head. Now, what is the essence of this motor? These motors are just to be able to enable the robot mimic the human facial expression. Now, it's not just seeing your expression and react intelligently to how you feel, but they can see your expression and create a sense of feeling of how you feel by replicating this expression on their facial looks. Right? Let's say, for example, you are conversing with this robot and you feel very sad. They pick your emotions from the camera and feed into the models and make predictions. And then they also replicate these emotions to make you feel like, oh, okay, this robot actually understands how I feel. Now, this is actually very nice. It's a very nice idea, seeing that the robot understands how you feel and they are able to keep you in that particular mood. Now, let's see another video of how a robot feels when you are feeling very bad or sad. Now look at this, look at the robot now. The robot feels disappointed because now this particular person is trying to have a conversation with this robot. and telling him how disappointed they feel. Now, this robot was able to react meaningfully to what the person said, not just by the face alone. You can see the gesture, the arm movement, and the body movement, and all of that. Now, they actually replicate what you are feeling, and they can actually present, and it will make you feel, good, and make you feel very welcome, kind of. All right, so let's look at facial expression engine. Now, how do we achieve this facial expression that is being performed by the robot? Now, we can achieve this by designing an actuators. Now, precise servo control for several body parts. Okay, let's look at the head now. We have designed servo controls that will mimic the eyebrow of a human, that will mimic the eyeballs of a human, and that will mimic the mouth and the cheek movement. Now, these actuators are designed such that they can handle the command that are sent from understanding the facial expression of a user. Now, we get this thing and send them to the actuators that will perform this facial expression on the robot face. All right. So we achieve expressive mapping. Now, translation of detected human emotion to appropriate robot responses. Now, not just creating robot smile, or make the robot raise their eyebrows, or make the robot turn their eyes or mouth movement to mimic what you're actually feeling facially. But we have great responses that will actually fine-tune what you are actually feeling into their vocal sounds. All right, we have anatomic modeling. Now, physics-based facial muscles simulations for neural expressions. Now, designing these facial expressions, we can also create a modeling in such that they're not just, but they have a real meaning of what you actually feel. All right, what you actually feel. And we calibrate these systems to act accordingly. Mind you, robots and machines, they are not humans that can actually do some of these things by default. So these things are actually calibrated to mimic fully what a user is actually feeling. Now, voice modulation systems. Now, the voice modulation, so we have prosodic controls whereby we can modulate the pitch, the tone, and the rhymes to mimic your voice and your tones to make it look natural and sounds very creative and intelligent. Now, speech synthesis, we use natural text-to-speech with emotion-aware voice generations. Let's say I'm feeling very sad, and we created models that can actually mimic these tones. Let's say my voice is very down. I woke up in the morning and I'm feeling very sad, and my voice is like, yes, how are you doing? And we have text-to-speech that can respond intelligently the way humans can feel and respond to situations and different emotions and different feelings at the given times and instances. Now, language synchronization, matching vocal emotions with facial expression. If I'm happy, the robot should be able to sound in such a way that it replicates what I am actually feeling at the moment. I am feeling very sad. I will not be happy. I will not be shouting. There's a way my voice should be like. The robot should be able to respond in accordance to my particular mood. Now, cultural adaptation. Now, the robot should be able to have a voice modulation pattern adapted to user cultural background. I'm from Africa. I'm expected that a robot should be able to respond to me in an African way so that I can relate to our conversation very well. Okay, we'll look at body language integrations. Now, when we look at body language integrations, when you're having a conversation, you don't just look at the robot will not just converse with you and just say things. I should have a good gesture that will represent, that will actually engage me in the conversation. So we design smoothie systems to actually emulate how human feels. The way I'm talking, I'm moving my hands, my head is moving. I expect that the robot should be able to do some of these certain things, move our arms, make gesture. I heard you tilt a little bit during your conversation. Now, this is actually designed to make all of this movement and the conversations. Now, gesture generation should generate a contextual appropriate hands and arm movement. I just explained that the robot should be able to move our arms during conversations and be able to engage with other parts of our body so that the conversation can keep going and making it look interesting. And again, I don't expect a robot to be able to have a conversation with me and it's getting so close to me. And because if it gets so close to me, when it's moving her arms and doing all that gesture and all of that, they might end up hitting me and create havoc and danger and all of that. So there should be a good proximity between the person the robot is conversing with. Just like humans, when you're having a conversation with a person, you cannot just go into the person. There should be a good proximity between you and the person that will actually keep the conversation going and make it good and intelligent. So we can also achieve that by creating good proximity between where the person is conversing and where the robot is, by using our environmental data, that is the scene analysis we talked about earlier, to know where the user is and where the robot is. I think we talked about this in one of our technical sessions, where a robot knows where it is and where the user is interacting with the robot. Their movement dynamics, speed, and fluence. A robot should be able to move with a good speed and accuracy. It shouldn't be lacking in conversation, because we want to have a real-time conversation with the robot, and its movement should be in sync with what the robot is actually saying. So we design some of this system to fit into conversation and be able to have a good movement and a good conversation with humans. So the question is, how can this capability be achieved in real time while maintaining high accuracy? How can we achieve all of this while maintaining a good speed and accuracy? Now, we're looking at how to achieve this. Now, technical performance optimization. To ensure an emotional aware robot operates efficiently in real-time environment, especially where human interaction is involved, several optimization strategies must be implemented. This include improvement in processing speed, data handling, and scalability. We all know that a robot that is actually conversing, and when you see a word, the robot responds after 10 minutes, will not really keep a conversation going. Before you know it, you as a user, you are already tired of conversing with the robot. It makes it look like the machine that it is. But for us to achieve this real-time conversation with a human, there are several optimizations that should be put in place to ensure that this conversation is achieved in real time. Now, one of the things is achieving a parallel processing. So how do we achieve parallel processing? How do we run our vision model, our large language model in real time without affecting the conversation? Now, we achieve this by creating a simultaneous executions in motion detection and language processing. Now, this actually helps us by creating a high and accurate processing of both the visual and the large language model. Now, how do we achieve this? Now, we create what we call multitasking for the robot. Now, in computing, we call it pipelining. Now, we split the tasks into parallel processing. The emotion is processing and written. That means we need a high processing computational power to be able to achieve all of this. While the robot is processing while the visual model is processing in real time, the large language model is preparing concurrently in separate processing pattern. Whereby this is achieved by using multi-threading or multi-core threading, whereby the model is running in a parallel processing unit, and whereby I can get the data of the facial expression predicted in real time and get the large language model being also communicating with humans in real time and fetching the emotions and all of that from there. Okay, another thing that can pose as a serious performance issue is latency reductions. Now, we can design systems that can actually surface for this latency. You don't want a robot to speak to you and you want to respond back. For the robot to respond back to you, it will take like 5 minutes and all of that. So we lock some of this processing in real time into several algorithms and host these machines in high computational edge processing device in real time. We can achieve this by hosting some of this model locally to be able to achieve real time. Because when you host this model locally, they are able to communicate in real time with your emotions and your facial without lagging through, without passing through the network challenge issues and all of that. Now, we also pass some of this model through compression algorithm like the LZ4 and the ZIP. This algorithm can actually suppress some of this because when you are running this model in real time, they generate several logs and they eat up memory. The memory suffers a lot. So we create some of this algorithm to compress some of this data and create a fast and efficient prediction and model. And we also use a cloud integration in a very high processing. This one is actually achieved when the processings are too high for the computing, for the edge computing to handle. Thereby, we can also leverage some of this cloud computing to hold some of this model and process and get feedback and all of that. So applications of these systems, we can apply this in healthcare service where patients' emotions are being monitored and be able to respond and treat patients to help them understand and keep them in the conversation, not just interact with robot and patients don't want to run away, they don't want to converse with the robot because the robot do not understand how they feel, but our systems are able to understand how they feel and interact intelligently with these patients and to help and create a safe environment for patients to interact with robot and all that. Now we can apply this in education. Educational robot, student engaging through emotion-aware tutoring. When the robot should be able to understand when a student is still in the game, when a student is no longer in the game, when a student is paying attention, when they are feeling sad, when they are feeling satisfied with what they are getting, and the robot should be able to have this conversation with the robot and be able to mimic what the students are feeling and help them to create a good learning atmosphere for students. And I can also apply this customer service in banks. They can relate with humans and understand how humans feel, how frustrated they are. They can also mimic this and create a sense of intelligent conversation with humans to keep them going and keep our organization going. In conclusion, the integration of computer vision and large language model create a powerful foundation for emotional intelligent robots by combining real-time emotion detection with advanced language processing and bidirectional emotion processing capability. We can develop robots that not only understand human emotion, but also respond with appropriate emotional intelligence. Thank you very much for listening. You have any questions? We are here to attend to your questions. And I've said a lot, trying to rush and see. We have more sections to talk about technical details of some of these models and how we can achieve these emotional intelligence systems in our everyday to-day robotics. So if you have any questions, you can put it in the chat box and we'll respond to those questions. So if there are no questions, thank you for joining and thank you for listening. We'll meet again next week Tuesday, as we look into other aspects of sessions and robotics and AI and other. Thank you very much.